Now that we've looked at the key principles involved in simplifying radicals, let's do a few more examples. So in this first example, we want to simplify a square root radical involving a variable, and we're told that the variable is positive. And the reason that's important is that we want to ensure that our radicand is a positive value so that we're able to square root this. We can only square root 0 or positive values. So if a is positive, a to the 7th would be positive, times 45 would be positive, and therefore indeed we would be square rooting a positive value. All right, so let's get on with the simplification process. We want to look for perfect squares in our radicand. So let's begin by breaking this radical up as root 45 times root a to the 7th using our multiplication property. And perfect squares that divide into 45, 9 would be the largest perfect square, which would leave us with 5. And a to the 7th could break up as a to the 2nd times a to the 2nd times a to the 2nd times a, which I could further break up as so. And then using my inverse property, the fact that the square root of a square gives me my x back again, I can simplify these sections. This is 3. This remains as root 5. The square root of a squared, as long as x is a positive number, that will be x. No absolute value needed. We only need the absolute value if our x was a negative, which we're told it's not. And the square root of a stays as it is. And then just cleaning this up, this stuff multiplied would be 3a cubed, and the root 5 times the root a can be recombined as root 5a for my simplified form. In our next example, we have the cube root of a fraction, or a division under the cube root sign, however you want to look at that. And so by our property, the cube root of a fraction, or the cube root of a division, is the cube root of the numerator divided by the cube root of the denominator. So I'm going to break this statement up as so. Now, there are no restrictions given on a and b, which is implying that a and b can be positive or negative. And if we think about that, all of this together, this multiplication and division, this entire red section, this entire radicand can be positive or negative in order to be cube rootable. We can cube root positives or negatives. So the restrictions on the variables, we don't need any restrictions on the variables is what I'm trying to say. All right. So I've broken my radical expression up, and I might notice that on the bottom, the cube root of 27 is a perfect cube, 3 cubed, so that's going to reduce to 3 on the denominator. And then on the top, I'm going to use my multiplication property to break the radicand up into sections. And then I'm going to further break up each of these by factoring out any perfect cubes I see. Well, with negative 16, I know that negative 8 is a perfect cube, which leaves us with the cube root of 2. A to the 5th, that can be broken up as a cubed times a squared. And the b to the 6th can be broken up as b cubed times b cubed, all divided by 3. So we then have the cube root of negative 8. That would be the cube root of negative 2 cubed. Cube root of 2. And then we have the cube root of a cubed times the cube root of a squared times the cube root of b cubed times the cube root of b cubed, all divided by 3. And my inverse property is here, 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 and here, meaning the cube root of negative 2 cubed, that will be negative 2. This section is irrational, so it remains as it is. The cube root of a cubed is a. The cube root of a squared is irrational, doesn't reduce. And each of these reduces to b, all divided by 3. All right, so if we clean this up, let's multiply together the rational sections. That would be negative 2ab squared multiplied by the cube root of, and since these are both cube roots, we can combine and multiply the radicands, 2a squared all divided by 3. There is my reduced form. So in the last two examples, what I was doing was simplifying my radical, that is, removing all the perfect nth roots, square roots, or cube roots from the radicand. In this question, what I want to do is I want to take my already reduced radical, my mixed radical, which has a rational part and an irrational part, and I want to turn it back into a full radical, an entire radical. So just before we proceed here, we have a restriction: x is greater than or equal to 0, which is important because it ensures that we can square root what's underneath the what's in the radicand. 7 times a positive number will be positive, so I can square root that. All right, so we can see that since x is positive, the value of this entire expression is negative. So I'm just going to leave the negative here. And then I'm going to reverse my inverse property. So when I see the 3 there, I'm going to take the 3 and I'm going to reverse it back into a square root, because that's what I'm dealing with here. And that means that that would have had to have been the square root of 3 squared. So the 3, before it was 3, was the square root of 3 squared. X squared would have been multiplied by the square root of x squared squared, and times the root 7x, which is already there. All right, so I have now returned everything to being under a square root sign, which means my negative just hangs out. I can combine these 3 parts in one radicand using my multiplication property. We have the same index, square roots, so we can multiply the radicands. So we have 9 times x to the 4th times 7x, which reduces to 63 x to the 5th, and the negative of that.